We continue to learn Chapter 3, Vector Spaces. Section 6, Row Space and Column Space. First, the definition of row space and column space. So if A given you an n by n matrix, which has m rows and n columns, the subspace of R 1 by n spanned by the row vectors of A is called the row space of A. So you consider each row vector and you do the span by these row vectors. This is the row space of A. And the subspace of Rm spanned by the column vectors of A is called the column space of this matrix. We can see this example. Given you A equals this 2 by 3 matrix, the row space of A is the set of all three tuples of the form alpha times the first row of A plus beta times the second row of A, which equals alpha beta 0. So this row space consider all the three-dimensional row vector where the third component is 0 and the other two components you can choose arbitrarily. Okay, and the column space of A is the set of all vectors of this form. So alpha times the first column plus beta times the second column plus gamma times the third column. So it will be alpha beta. So because alpha beta you can choose arbitrarily, so this column space of A constitutes in fact span the whole space of R2. For the row space and rank, we have such theorem. Two row equivalent matrices have the same row space. We can check the proof. So if B is row equivalent to A, then B can be formed by a finite sequence of row operations from A. Okay, thus the row vectors of B must be linear combinations of the row vector of A. In consequence, the row space of B must be the subspace of row space of A, right? Because B is formed by a finite sequence of row operations from A. We know the row operations, you can interchange the two rows. You can use a non-zero scalar times one row of A, or you can use a scalar C times one row, then add to another. Okay, so this means all the rows from this matrix B, comes from the rows of matrix A. Okay, so the row space B must be the subspace of the row space of A, can obtain from the rows of A. Okay, the span of the linear combination of the row space of A. And since A is row equivalent to B also, so the row space of A must be the subspace of the row space of B. And then we know A and B have the same row space. Okay, now we consider about the rank. So the definition for the rank of a matrix A is the dimension of its row space of A. We have this definition. So to determine the rank of a matrix, we can use these procedures. We reduce the matrix to row echelon form. The non-zero rows of the row echelon matrix form a basis for the row space. And the number of non-zero rows is hence the rank of this matrix. So this gives you a procedure to find the rank of a matrix. Do the Gaussian elimination to reduce this matrix to row echelon form and find the number of non-zero rows. This is the rank of this matrix. Moreover, we know also that the non-zero rows of the row echelon matrix form a basis for this row space. Example, ask you to calculate this rank, the rank of this matrix. Then we just use Gaussian elimination to transform this matrix to its row echelon form and find its number of non-zero rows. This is the rank of this matrix.